Thanks very much, Leighton. That was terrific. Look, I don't know how old you have to be to remember Towering Inferno, but I was quite young when it came out, so maybe you have to be quite old. I don't know. Anyway, nothing on tall buildings would be complete without someone who knew something about fire, and we're very fortunate to have here today not someone who just knows something about fire, but someone who's actually a world expert. And you will know from just reading the newspaper that facades and fire have been very much in the news recently. So it's with great pleasure that I call on Jose Torero to present Fire and Facades. Thank you, Jose.
Thank you very much for the kind introduction, and as you can see, I changed the title of the talk. In the paper that you have, it only says facades, and I try to keep my abstract as brief as possible, because every time that I explain what I do, then I get disinvited to give this kind of talks. Nobody seems to want to look at the elephant in the room, and here is a very, very big elephant, as you can see from this picture. So I think we've got to the point where today we have accepted the fact that big fires associated to facades has become literally a feature of modern architecture. Now, you mentioned Towering Inferno. This is the fire that actually inspired Towering Inferno, and is the Andraus building in Brazil. And as you will see, so this is a tall building built in the 1960s, and where a fire happened, and as you will see afterwards, the fire propagated through all the external cladding, and very rapidly involved the entire building. So this type of fires were very, very common in the 1960s. And as we can see, they were enormous consequences. So in this particular building, there were several people that died. They were actually in the hundreds, and it was the inspiration for Towering Inferno. So we realized in the 1960s, and basically as a function of every fire that actually has a name happened in that period, that this is something that needed to be avoided. The entire strategy to try to guarantee life safety in tall buildings depends on the fact that fires should be contained to a single floor. If we cannot contain a fire to a single floor, then the entire fire safety strategy collapses. You know, from the pressurization of the stairwells, which is a very complex process as was described before, from the structural integrity, everything depends on the fact that we can contain the fire within one floor. So a scenario of this nature is actually completely unacceptable, because it dismantles integrally the fire safety strategy. So we fixed the problem. And in the 1970s, we came up with a solution to the problem. We dimensioned the separation between windows. We put strict criteria on material flammability for all claddings. And we created a system by which we test, using fire resistance methods, the separation, so that internal fires could not propagate upwards or downwards. So as you can see in that picture there, that's World Trade Center 7. And despite the fact that this building burned for about 8 hours, the fire spread was only horizontal. There was no vertical spread of any nature. So as you can see, we managed to fix the problem. So we came up with solutions that effectively guarantee that this was not going to happen anymore. And this prevailed until the early 2000s. Then what happened is what you can see there. So this is just a sequence of a few of the fires that have happened in the last 10 years, and it covers the entire world. So there's photographs from Europe, from the United States, from the Middle East, from Asia, from Australia, you name it. So now they're happening everywhere, to the point that we don't even notice them anymore. Many of them don't even show up in the newspapers anymore, because it's an accepted fact that these are the kinds of things that we're going to have with modern facades. Modern facades have become incredibly complex systems, And the systems, because of their complexity, have become misunderstood. And all of a sudden, we are back in the 1970s. There's another example of a 1970s fire, the Joelma's fire, also in Brazil. And again, a tragic event that effectively landed us in a very awkward position. So I think really this is a true question that we need to ask ourselves, is how we landed back in the 1970s. And worse than that, how did we become completely incapable of dealing with the problem to the point that we have to stick our heads in the sand and pretend that the problem doesn't exist. So the problem exists, is real, and the consequences can be quite dramatic. So what are the key changes that have brought us into this position? So basically, every time that we've innovated technologically, we're going to introduce risks. Many times those risks are very managed and we understand them very well. But from the inception of modern construction, we've introduced things like what we see in this image. So basically the introduction of steel into construction resulted in a major problem. The steel actually did not behave as well as timber. So timber became the reference, and we started to try to develop methods to try to make steel as performant as timber. Now, we succeeded at resolving the problem, but that's what it took. We had to study the problem, understood it, and then move on to try to propose solutions. So what has changed? Basically, our building envelopes have changed dramatically. So we don't have the same type of systems that we had in the 1970s or 1980s. We have introduced all sorts of novel construction methodologies, and we've made all sorts of statements about all this complexity of the structural systems and all the different things that we're putting in place. Now, we have introduced massive amounts of flammable insulation materials under the name of sustainability or green buildings. So basically, our entire facades are protecting us now from heat transfer. So effectively, we do that by means of the introduction of cellular plastics, and we has forced us to change the paradigm. We're not talking about flammability anymore because the materials are flammable by definition, but we're talking about encapsulation. So we're protecting flammable materials by means of external barriers. So there's a massive change in paradigm that we really haven't understood very well, and I can keep going, and the list is very long. So there's a number of different things that have happened in the process, and the first thing that we need to recognize that it's not one problem. All those images that I show, if you actually analyze the fires, in every single case you get a completely different scenario. So the analysis of these fires shows that what we have is a multiplicity of problems, all embedded in the concept of the modern facade design. So we design facades in a completely different way, and in the process we have introduced a multiplicity of problems, and we cannot box them into one single problem. There's numerous problems that need to be analyzed in great detail. So if you look at conventional facade design, this building, despite being a very modern building, that's the Aqua building in Chicago, shows in a very explicit manner the way in which we did things before. We put a barrier. So here's our concrete slab, and our concrete slab becomes a barrier between one floor and the other one, and that barrier is the one that I need to design to guarantee the protection. So how do we do that? Basically, we provide fire resistance to this barrier in such a way that the fire can burn out and that fire cannot penetrate this barrier. We create geometrical constraints to the external cladding that include both flammability of the external cladding that sits on the barrier and that prevents the flames from breaking into the upper floor. So by introducing an appropriate geometry, producing proper flammability criteria, and putting a barrier, we are preventing a fire from entering the interior of the building or a fire from entering from the exterior of the building. Now, that changes completely when you change the building envelope and you create a situation like this. Once you have a continuous building envelope, what you do is basically stop the barrier short from getting into the external facade. The moment that you do that, what you do is you create a weak link in this point. Now, you might think that this is about filling the gap, and filling the gap to the same level of resistance as the concrete slab. But that's not the case, because here you have a very lightweight structure, you have a much heavier weight structure, and therefore you're going to create massive relative displacements. The moment that you get massive relative displacements, then this gap starts deforming, it starts creating gaps, and allows the penetration of the fire internally. So here you have an example of a problem that we have created by transforming components into a system. So now what we have is system behavior, we don't have component behavior. In the past, basically I guarantee geometry, I guarantee flammability by testing components, and I guarantee fire resistance by testing components. Now I need to be able to understand the system in its integrity. And if I don't understand the system behavior, then I won't be able to address this specific problem. So this is how we went from here, which is a perfectly controlled problem, to here, which is a completely uncontrolled problem. In other words, what we did, we changed the problem. So the moment that we have a facade of this nature, and I have nothing against Norman Foster, by the way, but I like his buildings, so I put them always as examples. And this is what you're creating. So what you have is a system that is a structure that is heavyweight, that is going to heat up very slowly, and it's going to deform in a very peculiar way. That's the concrete slab. Then you have a lightweight system that is going to deform in a completely different way, and then you have a connecting point. That connective point is going to result in, basically, in the presence of a fire, we're going to try to block this by introducing some sort of a barrier. But the truth of the matter is that if I put a fire, what I get is relative displacement. So this is going to rotate in a certain way due to temperature gradients that are produced in the concrete slab. This is going to rotate in a completely different way because it's going to be restrained thermal expansion due to literally just simply dilatation of the steel or whatever the material is. And the result is that you get two systems that are displacing themselves in a completely different way. The result is the production of a gap. Now, how do I fix that problem? Okay, and this is not the way in which we fix the problem. Now, detailing becomes very important. Detailing, quality of workmanship becomes very important, but also integrated design becomes very important because it's now the structure plus the facade that matter. Now, if you look at this picture here, this picture is one of those pictures of a problem that cannot be solved. You have the two connecting elements, you have the very lightweight system, you have the concrete slab, and the concrete slab lands on the glass. So how are you going to fix that problem? Once you created that system, then you cannot fix it anymore. Now, how did we land in that position? The facade designer designed the facade, the structural engineering designed the structure, and nobody worked on the system as an integrity. Then we tried to fix it by filling the holes with whatever we want, but there is no way you can guarantee continuity when you have that type of a system. So filling the opening is really not the solution because relative displacement will never allow to fill that opening. So effectively we have created, because of poor construction detailing, we have created a problem that cannot be fixed, and this gap can never be resolved. So at the end of the day, what we're talking is about complex building systems. We're not talking about components. And if we don't really understand these complex building systems, we are going to be always in the situation where we cannot fix the problem. Now, the complex building systems introduce an enormous amount of detailing. So we have all sorts of different components that go into the systems, and they're getting more and more and more complicated because we're putting more and more demands on the systems. Now, the complex building systems are multi-purpose. We want them for energy conservation, we want them for stability, durability, comfort, life cycle, you name it. We've created all sorts of different requirements for those systems. Now, those systems are going to be more and more dependent on labor skill and on cost. There's a lot of tolerance issues, installation issues, times, because we want them fast. They all have to come up really, really rapidly. We have all sorts of modifications that are done during construction, and all these things are affecting the performance of the system itself. None of these things were taken into consideration. The objective at the end is to guarantee that encapsulation. Then this is the problem that needs to be solved, because we are putting flammable materials in the systems, and therefore we need to encapsulate it. So let me give you the example of the kinds of things that we are encapsulating and the kinds of problems that we're generating. So if you look at these two images here, I'm going to show you two videos. One of them is the typical two aluminum plates with polyethylene in the middle. That's everywhere. So today we have all these facade systems that have these two aluminum plates, and you have a plastic in between. Okay, why do we put the plastic? For a number of different reasons, from minimizing vibrations to insulation issues. So now, what happens when we start heating this up? What is the failure mode? The failure mode is the two aluminum plates, and then you have in the middle this plastic, and as you start heating up, you're going to realize that the way this fails is not because you're igniting the plastic, but because the adhesive between the two of them fails, and then it splits. So the moment that you have thermal expansion of the aluminum plate in the front, and that it cannot be absorbed by the cold back, then you get relative displacements, the adhesive fails, then you get a split. The moment that the split happens, what ends up happening is that then it starts gasifying, and then the result is that it ignites. Now, it's going to take a little while. You can see how it's beginning to split now here, and the moment it starts splitting, you can see the smoke being produced, and then all of a sudden, you get the ignition of the material. You see how it's splitting? So once the material ignites, then it just goes. Now the concept of preventing upward flame spread disappears completely, and all of a sudden you have flames that are coming up from the outside. You know, other ways of doing encapsulation, let me show you another video, is by actually introducing a ceramic rendering that goes on top of the flammable material. So this is a common material called Dekpo, and basically what you have is, again, you have a plastic material in the back, you have in the front ceramic rendering that is impregnated into the material and basically protects the material from a fire. Very rapidly you see the mechanical failure. Again, it's thermal expansion that creates the crack, and then the moment you get the crack, then the flammable material starts gasifying, and the result is that you get flame that ignites. Once the flame ignites, then this whole thing is gone because you have exposed an excessive amount of fuel that is going to sustain very rapid flame spread. Now, here you have a very, very complicated problem. You change flammability for encapsulation. So what you're looking is into the capacity that this layer that you're putting in front has of protecting a flammable material. So it has nothing to do with flammability. It is purely a matter of having a protective layer. The encapsulation is the problem that we need to solve. So if we look at it, then basically we're talking about protective layers, and what we want is to be able to create a protective layer that actually does the job. Once again, a system behavior. It's not a material, it's not the flammability of what we have in the back. So you can put all the fire retardants you want in the polyurethane material that you have in there, it's going to burn anyway. Okay? These materials, no matter how you retard them, they are still going to burn. The problem is that we have encapsulation. That's the way we fix the problem. So we have to be very careful in the way we design that encapsulation. So the question really is, how do we establish the performance of encapsulation of protective layers? Okay? So it is not about the material flammability, but it is about the encapsulation. Now, as you can see, we've created all these problems, and we understand what the problems are. We encapsulated these materials because we know they are flammable. There's no way to circumvent them. That's why we encapsulate them. So we've created systems that are quite complex in nature, and to be able to fix the problem, you need to be able to test the problem that you're trying to solve. Instead, what we're doing? All over the world, we have flammability tests. So all our materials that go into facade designs have to meet these flammability requirements. Needless to say, if I utilize EPS, or I utilize polyurethane, or I'm going to use, for example, polyethylene, they're going to fail. That's why I encapsulate them. So why am I testing them for flammability? If at the end of the day I know they're going to burn. So nevertheless, that's what we do. So we comfort ourselves and feel very happy because we've tested them for flammability. Okay? Then we say, well, some people are a little bit more progressive, and you know, they move along and they say, well, let's do fire resistance. Fire resistance is to test the resistance of a non-flammable material to the impingement of a flame to establish a barrier. These things are not a barrier. So then we say, oh, let's just require fire resistance ratings. Let's put FRLs. And we test them against fire resistance. Needless to say, they're going to fail. They're not designed for it. So then we say, oh, well, no, let's just not do fire resistance anymore. Let's move somewhere else. Okay, and then we go to other different things. Because these tests, we realize, are not there to test the system performance. They're not there to test mechanical behavior. They're there to test a barrier. Now, when we had a concrete slab that served as a barrier, that made sense. But now that we have a connecting point and we have a complex system, it doesn't make sense anymore. Nevertheless, we keep doing it. Now, then when we finally realize that none of these things work, then we say, let's do scenario tests. So do we test for wind for one wind condition? There you go, one wind condition. Do we test for wind without putting any instrumentation? There you go, no instrumentation. But we're happy now because we're testing against one scenario. If I'm a manufacturer of a facade system, I'll be very happy because I have a very easy target. Does that fix the problem? Not really. So that's what we're doing today. We have all these tests, but we never ask ourselves the question if these are the right tests. And the problem is that nowadays, we started here and we've lost this completely. So we have to start thinking on what is the solution. Now, the problem is that the solution is truly adequate testing. And adequate testing, we do know how to do it. We know it perfectly well. Okay? So we know exactly what needs to be done, but it requires bespoke testing that is basically for each particular system. It's not a standard test. Each system is a system of multiple components that requires a testing methodology that is directed to solve the problem, just like you do with a wind tunnel. Okay? But we're not willing to do it when it comes to fire because we're not willing to address the system behavior. We want a standard test. We want something that is good for flammability, that is good for fire resistance, but is not good for a system behavior. Okay? So at the end, we need to be able to address building plus envelope, and that requires bespoke testing for each particular system. So we need a testing methodology. So if we really think about it, the past is one test for all materials. What we want is a bespoke methodology for each system. Okay? That is going to cost more? Of course it's going to cost more. But if what you really need to do is fix the problem, then that's what is necessary. So today, this is what we need, bespoke test protocol for each system. Now, at the end, let me ask you the question. So if you want to use encapsulated EPS, do we know how to fix the problem? Yes, we do. But it really takes a lot of effort. Because the problem with EPS is that EPS melts at a very low temperature, so it starts retracting. So your protective layer loses its structural integrity because it has no support. Okay? So we need to design in a way such that we prevent that melting. Now for that we need to try to understand the different forms of EPS and see at what temperature it degrades in such a way that I understand how to prevent that from happening. Then I need to provide systematic testing by which I expose the different types of barriers to an array of different conditions, not a simple scenario test. Once I understood this, then I can start looking into the potential fire scenarios and see where is the match, and then reproduce with large-scale testing, those scenarios until I actually get what I want. Those tests have to be properly instrumented, and they will serve as validation for the whole methodology. So, can it be done? Of course it can be done, but it takes a lot of effort to do it. Now, the question is, if we want EPS encapsulated in our facades, then yes, we can do it, but this is how far we have to go. Now, if you want to ignore that and just basically use EPS without really thinking about it, then we're going to continue to have these facade fires inevitably. There's no way to prevent it. Okay? So, do we know how to do it? Yes, we do. Okay? We have the methods, we have the understanding, we have the instrumentation, we know exactly what needs to be done. The problem is that that requires to change the way in which we think. We don't have standard tests for this type of problems. What we have to have is a bespoke methodology that enables us to resolve the problem that is at hand. So what seems to be a very viable technical proposition is truly an enormous philosophical drift. And that's the problem that we have today with facades. The reason why we have so many of these facade fires and the reason why we're going to have still so many of these facade fires is because we have not made that philosophical departure to try to think of this problem in a different way. It's not a material problem, it is a system problem. And until we accept the fact that we're dealing now with systems, we're not going to be able to solve this problem. Thank you.